So simple. Okay. Oh, I forgot. I have to share the screen so you can see what I'm seeing. Oh my goodness. Yeah. Okay. So can you see, oh, can you see what I'm sharing? Are you able to
Yes.
see the page? Okay, good. So let me make this bigger since you're actually speaking. Um, let's see. Oh, yeah, so you have a little summary here telling you how the intermolecular forces influence different characteristics, right, of the chemical, physical and chemical properties. Mostly physical, but yeah. Okay, so these are listed right here. So, you said number two, was it two and three?
Yes, correct. 2 and 3.
Okay, so draw Lewis structure for hydrochloric acid, ethanol, and hexane. Which of the following liquids above are soluble in water and carbon tetrachloride or both? Oh, okay, because we haven't done that part yet, so that will be a little bit of a struggle.
Okay, I'll wait.
Okay, and then three, let's see. Oh, we can do three because we did three. Indicate which of the following properties will increase, decrease, or remain constant or unaffected by the increase in the strength of the intermolecular force. Okay, we can do three because we've covered three. So
Okay.
in three, let's see. If you increase the strength of the intermolecular forces, so the molecules are trying to stay more together than to move apart. Which one will increase, decrease, or remain constant? Okay, yeah, we did all these three, so you can do that one. So imagine, ooh, so what did I do? Imagine, once again, I like having a visual for me personally. I like having a visual. So I'm going to be drawing a container here real quick. We have a container, which I'm going to be drawing with my mouse right there. And you have molecules that are attracting each other more. And there's more of them attracting each other because they have greater intermolecular forces, right? So they're kind of more connected than necessary. And so if you have an increase in intermolecular force or the strength, which one will increase, decrease, or remain constant? So you want to examine each one at once. If the intermolecular force, if IMF is high, what does it do to the vapor pressure? Do you have more vapor molecules or do you have less vapor molecules?
You should have more since it increases it because you're hitting it. You're putting pressure on it, so it should cause
Okay,
more more vapor.
okay. I see what the issue here is. Okay, so yesterday we talked about the molecules and the pressure, right? So I'm going to write up here, right? But the number of molecules are directly proportional to the number of pressure. So I'm talking about the value of pressure or the magnitude of pressure. So number of vapor molecules, not just molecules. So the more vapor molecules you have, the greater the pressure, right? Because the vapor molecules influence the pressure. Because remember, the pressure is formed when these molecules bump into the container. So if you have molecules in the vapor form, and we are only looking at the ones in the vapor form, if the molecules manage to escape the liquid and form vapors, then if you have more vapors, you have greater vapor pressure because these molecules are colliding with the wall. And that's how the pressure is created. Now imagine this container is covered. So now I ask my question again. If you have an increased strength of intermolecular forces, which means the molecule in the liquid state are being drawn back into the liquid, they're being held back, they're being prevented from leaving the liquid, would you have a higher vapor pressure?
Okay. No, it would be no because
Okay.
yeah,
Yeah,
'cause more
in
pressure.
1312, you don't want to rush to give the answer because most of the time you're mishearing the question or you're jumping through, you're skipping steps you should have thought through, right?
Yeah.
Yeah. If you're increasing the intermolecular force of attraction, molecules are being held back. So I try to dramatize this in my head like extra, like the molecules are being chained back. They can't leave. So if they can't leave the liquid, they can't form a vapor. Because remember, the vapor molecules are different from gas molecules. Gas molecules were always free. Are always escaped. They're former liquid molecules that escaped. So if the force holding them in the liquid is strong, you're not going to have a lot of escapees, right? So you're going to have less molecules in the vapor form. If that's the case, the pressure is less because only few molecules can escape. So, right? The force, you're going to have a decreased vapor pressure. Why? Because you have only few molecules that escape. Because remember, vapor molecules are escaped liquid molecules. Decrease for the first one. So that part is done. The second one, boiling point. I don't think we've gotten to boiling point yet. We're supposed to discuss that today. Well, since we're here, let me at least finish that thought, okay? So with boiling point, let me go ahead and see I'll draw it right here. The way boiling point works is this. The boiling point is the temperature at which the vapor pressure equal the atmospheric pressure. So what we call boiling point is temperature at vapor pressure equal atmospheric pressure. Okay, so we're still back talking about the vapor of the liquid, the escaped liquid molecules. Remember those vapors? We're still talking about those. And these vapor pressure, there has to be enough molecules released from the liquid, breaking free from the liquid, so that the pressure above the liquid, the vapor pressure, matches the atmospheric pressure. So for us to get to that next level of thought, we have to define what exactly is the atmospheric pressure. They tell us here we're looking at the normal boiling point, 1 atmosphere. Okay, so let's examine atmospheric pressure. Can I write? I need a little bit more space. Let me look over here. Let's say we have a container, okay, over here to the left and a container to the right. And I'm going to draw the atmospheric pressure in terms of molecules. So the atmospheric pressure is usually 1 atmosphere, okay? Once again, I like to use visuals to illustrate this. And then the number of molecules, let me make it 10. So for us to experience 1 atmosphere of pressure, we have to have 10 molecules of gas surrounding us. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, this is 5, 6, 7, 8, 9, 10. Okay, I got to 10. Now imagine these are the gas molecules in the atmosphere producing that 1 atmospheric pressure. Okay, the definition of the boiling point is boiling takes place when the pressure in here, the vapor pressure, okay, I'll call it pressure vape, when the pressure in here matches this pressure here. When these pressures match, then we see boiling. The temperature at which that happens is when we actually see boiling. So over here on the left, I'll just say this is the regular container. Regular. In the regular container, let me say we are at boiling. Okay, so we are regular container at boiling. So at boiling, you have some liquid molecules right here, liquid, and then in the gas, you have, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This picture I have on the left is currently boiling. How do I know it's boiling? You have to count these vapor molecules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the number of vapor molecules match the atmospheric molecules as far as the pressure, right? Remember, the pressure is caused by the vapor molecules colliding with the wall. So when the vapor molecules begin to produce a pressure that matches the atmospheric pressure, this is boiling. Okay? Now, what is happening in the container on the right? The question said somehow something happened to increase the intermolecular force in the liquid. So now in the liquid, you have molecules, right? But you have an increased intermolecular force. So back to the question again. Do we have more or less molecules in the gas phase?
we will
What
have um less less
less, right?
molecules.
Less. So at the same temperature that caused the container on the left, the liquid on the left to boil, at that same oh, it's supposed to be boiling. What is that? It's supposed to be boiling, right? The same temperature that caused the liquid on the left to boil will not boil the liquid on the right because at this level, at the same temperature, let's say it was 100 degrees Celsius because we are more used to that temperature. At 100 degrees Celsius, the temperature, the solution on the left, or the liquid on the left boils. The liquid on the right will not boil because you have less molecules in gas phase. We need 7 more molecules to get in gas phase to cause it to boil. So normally what we do at that point is, if possible, you increase the heat and take it higher to make more molecules break free from the liquid phase and go to gas phase. They didn't ask you all that. What they're asking you here is what will happen to the boiling point, right? So if you want the container on the right to boil, or the liquid in the container on the right to boil, you have to actually increase the heat, right? If you increase heat, you have more molecules escape. So more vapor escaping, until you get to that threshold, the minimum requirement, which is get to 10. When you get to 10, the molecules colliding with the wall produce a pressure of 1 atmosphere, and then at 1 atmosphere, we start to see boiling. Okay, so the way to fix that is to increase the boiling point. So now we go back to the question. They're asking you, what will happen to the normal boiling point? If the goal is to boil, you have to increase this. So this would be increase. Does that make sense? The normal boiling point will have to be higher. Okay. And then we talked about this yesterday. Heat of vaporization, the heat required to make the liquid into a gas, right? So back to this scenario again. If you have more attraction between the molecules in the liquid phase, then you're trying to make the liquid into a gas. That's what heat of vaporization is. Do you need more heat to help the liquid molecules escape, or do you need less heat?
You need more heat.
You need more heat. So the first one will be decrease, second one will be increase, third one will be increase. Okay. That's why I like to refer to the vapor molecules as escaped liquid molecules, because they weren't always there. They escaped from the liquid versus regular gas molecules that were always there in the gas phase. They're not former liquid molecules. Okay. So the goal is, what can you do to help the molecules escape? If the bonds holding them back are stronger, there's going to be less of them escaping. If they're weaker, there's more of them escaping. Okay. So let's go ahead and go over the chapter. That way we can make some progress, and then we'll see if we can revisit this, if it's necessary to revisit this. Okay. So I won't close that completely. Y'all, you know how I have so many pages open. I'll do that. So let's see. So let's continue here. Now, in the slide 60, it talks about vapor pressure versus temperature. So we're looking at how temperature influences vapor pressure. This is the bottom line of this slide. We're told increasing the temperature increases the number of molecules that are able to escape the liquid. Remember, those vapor molecules are escapees. They escaped. So if the goal is to increase vapor pressure, then apply more temperature. So this essentially explains what I just told you, only this is in context. The net result is that as the temperature increases, the vapor pressure increases. So this is one of those things that you want to write down as you're taking notes. Like I told you, in the PowerPoint slides, you have some words that are bolded. Those tend to be the bottom line, kind of like the hashtag. If there's anything you have to remember walking away from this slide, it's usually bolded or a different color, right? Greater temperature on the liquid or applied to the liquid gives the molecules in the liquid form a greater chance to escape to form vapors. Okay? So this is showing you here that the rate of escaping is not even linear. That means that when you increase the temperature, it's not a linear relationship. So, say for example, that's what this graph is showing you here. Exponential graphs are different from linear graph. If it was a straight line like this, that would mean that say you had a liquid, okay, releasing 20 molecules of gas, and this liquid was at room temperature, let's say 25 degrees Celsius. Then if you made the room hotter, you doubled it to 50 degrees Celsius, then you double the amount of molecules released to 40 molecules. That would be true if the graph was linear. You have a linear relationship. But we don't have a linear relationship. We have exponential relationship. And if we've learned anything in the time of Corona, is the value of exponential growth, right? Which they've been showing on TV. I'm like, man, they explain those graphs. Okay, exponential growth means you don't have a direct relationship like that. If you double the temperature, you may have like 200 molecules released. So there isn't a direct relationship. It's not direct like that, where you double this number and you double the amount. When you double the temperature, you get more than you expected to be released. That's what it's showing you right here. Okay. So the vapor pressure, oops, sorry. The rate of growth, once again, depends on the strength of the intermolecular forces. So if you have stronger intermolecular forces and you're trying to apply a heat to accomplish something, you have to apply more heat. Okay? This shows you once again the graphical relationship. You see how you have to apply a lot of heat with water? Because remember, water has that hydrogen bond. Not only hydrogen bonds, it has two hydrogen bonds. So it's twice the amount of hydrogen bond. Hydrogen bond times two. So look at how much heat you have to apply to boil water. A lot. Ethyl alcohol. Alcohol only has one hydrogen bond. That ethyl ether only has dipole-dipole and London dispersion force, right? Remember this one here? Alcohol here has London dispersion force, dipole-dipole, and just one hydrogen bond. Water has London dispersion force, dipole-dipole, and twice the strength of hydrogen bond. I shouldn't even say twice because remember it's exponential, so it's not really a linear relationship, but you get the idea. Ethylene glycol, man, we haven't, ethylene glycol didn't even make the chart. It started to, but somewhere here, if you zoom out even further, you will see where ethylene glycol is, right? What it takes to boil it, what it takes to freeze it. It impresses me that some people see this graph and they're able to monetize it, right? Take ethylene glycol and make it an antifreeze. And so come a cold winter day, it doesn't freeze easily, it doesn't boil easily on a hot day. I look at this graph and all I see is science. I'm trying to see business when I look at a graph, like science and business. It's just so hard to switch my mind. So hard to learn, to try to monetize the stuff that I know. Okay, so finally we're here and we're looking at boiling point. You see, I told you we hadn't covered it yet. It's okay, you get to cover it again. Boiling point, we're usually talking about temperature. Towards the end, we'll see that there's more to boiling than temperature. Okay? Essentially, the boiling point has to do with both temperature and pressure. But for the most part, if somebody asks, ooh, okay, so I'm not spelling right when I'm talking. Pressure. If somebody asks you, what's the boiling point of water? The answer most people provide is 100 degrees Celsius, and they stop talking. They don't say 100 degrees Celsius at 1 atmospheric pressure. Technically, the answer is true if you are at 1 atmosphere pressure, right? So boiling point of water is 100 degrees Celsius when the pressure is 1 atmosphere. But we only naturally provide the temperature unit only versus the pressure. Okay, we're told here when a temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, the vapor bubbles can form anywhere in the liquid, not just in the surface. This phenomenon is what we call boiling. and the temperature at which the vapor pressure equals external pressure is the boiling point. So this is summarizing what I said earlier, that the boiling point is the temperature when vapor pressure is equal to, they call this external pressure, they're trying to be non-committal. I just call it atmospheric pressure. Okay. At our level, we're not doing experiments in an enclosed container. Of course, when you get to upper level chemistry, you want to understand it doesn't necessarily have to be the atmospheric pressure, it has to be the pressure of the environment close to the container where boiling is taking place. You can actually modify the boiling temperature by modifying the atmosphere around the container. And there have been YouTube videos about this, you know. But yeah, get the pressure in here in the container to match the pressure around the container, and you get boiling. And so I saw some students do this on YouTube without even heating the solution or the liquid. They just took the container, put it in the vacuum, sucked out the air, and then the liquid started to boil. And I'm like, oh my goodness, this is sweet. Okay. So as long as the vapor pressure can rise and get to the atmospheric pressure, boiling happens. But you have to make the pressure first, right? The vapors. The vapors have to be made. If they're going to be made, they have to be free from the liquid, right? Because remember, for the vapors to be here, vapors are liquid molecules that escaped. So they have to be free from the liquid, get to the vapor form. And then when they get to that form, they're actually able to then influence the boiling, right? Boiling happens at this point. Any questions about boiling?
No.
Okay, so remember how you asked me how do I know normal boiling? Okay, normal boiling goes with 1 atmosphere pressure. Normal boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals the standard atmospheric pressure, which is 1 atmosphere. So your liquid molecules escape, form vapor. These vapors begin to collide. So we're talking about what's happening above the container. So imagine this container is sealed, right? You have your liquid here, you have your vapor slash gas phase. These molecules have escaped. They begin to collide with the container. As they collide with the container, that's when the pressure is being generated. When that pressure equal 1 atmosphere, we got boiling, and we begin to see this happening. Okay, that's why whenever I was younger and I was cooking way younger, and I left the pan open, my mom would say, "Cover the pan or whatever." When I was cooking and I didn't have a lid on the pan or the container, she'd come and say, "Cover it, or else it won't boil." It would take very long for it to boil and you're wasting electricity. And I'm looking at her like, okay, mother. Now, my mother doesn't know this rule, the definition of boiling, but she understood the principle that if you put a lid on the container, the gas molecules don't escape. So many of them are there creating that pressure that you want. If you leave the lid open, if you're having some kind of soft boil, it takes longer for the pressure above the liquid to reach the atmospheric pressure, right? Yeah. Anyway, so once again, somehow if the external pressure is lowered, you lower the boiling point. So the people who were doing the video on YouTube did that. They took the container, put it inside a chamber that could be evacuated. And then they sucked out all the air of the atmosphere. So this became the atmosphere, right? The surrounding atmosphere. They reduced it, they lowered the pressure by removing the gas, lowered pressure. So by lowering the pressure, the way I paraphrase this is they lowered the standard. So if this originally had a lot of gas molecules, in that case, the liquid in here will have to have, let's see, 1, 2, 3, 4, 5, 6, 7 gas molecules to boil. By them evacuating some of the gas from around the container, they ended up with fewer gas molecules. Now the standard the liquid has to reach or the vapor has to reach is much lower. I'm just going to leave 2 molecules here for illustration, right? They went from 7 molecules being the standard, now we're down to 2. So all you need now for boiling to happen is 2 molecules in the gas phase, and bam, boiling happens. They were able to do this without actually heating the container, and then you could see the liquid boiling, and I was like, man, that's impressive, right? So places that have lower pressure, such as Colorado. Colorado is elevated, right? And the idea is when you go to a place that has a higher elevation, it generally has a lower atmospheric pressure. There's less gas molecules in the area, so there's lower atmospheric pressure. So that just means the standard that the vapor phase has to reach is just lower. So I moved to propose that if you're trying to boil water in Colorado versus boil water in Texas or somewhere where it's a lot deeper, maybe like I want to say Nevada. Is Nevada? Yeah, I think it's Nevada. Somewhere where it's a lot lower than sea level, right? Where the pressure is higher, it would take less energy to boil water here. Most of the time, they have a question like this when you go up a mountain and trying to boil water. I'm like, if I'm going up a mountain, I am not trying to boil water. The point of that question is to say, if you're in an area where the atmosphere pressure is lower, at what temperature can you boil water or an egg? If the standard is lower, you need less heat to boil the liquid. Okay? Yeah. Now moving on to Clapeyron equation. This is the one we're talking about yesterday when we did the question. Remember that question? This shows the relationship between the vapor pressure. The vapor pressure here is written as PVAP, vapor pressure. That's the symbol. The pressure of the vapor versus the gas pressure will be P gas. And how it relates to temperature. I told you before, the relationship we saw earlier was not a linear relationship. It was more like a exponential relationship like that. Okay? It's hard to make predictions with that kind of relationship. Plus, I personally think that chemists have a preference for straight line graphs. Okay? So even though we saw earlier that there's a curve, they're like, nah, can we make that curve into a straight line? So if you want a straight line relationship between pressure, vapor pressure, and temperature, this is it right here. They had to modify, of course, the measurements to get it to be a linear relationship. So they took log natural of the vapor pressure and drew the data points. So you get your data points of the vapor pressure in millimeters of mercury, and then take the log natural of that, draw it against the inverse of temperature. When you do that, you actually get a linear relationship. And with a linear relationship, it's a lot easier to make predictions about new scenarios. So we're looking over here and you see now you have log natural versus inverse of temperature. And you can see as the temperature, as the inverse of temperature increases, the log natural, as we're going to the right, the log natural of the vapor pressure decreases, right? Here you have a smaller value of 1 over T, but a larger value of log natural P. Over here, you have a larger value of 1 over T, but you have a smaller value. So you have an inverse relationship. So what is this useful for? You're wondering, like, why are we learning this? Are we just learning about the graph to figure it out? Well, when you're in the lab, being in the lab is all about data collection, right? Getting to experience science. But one of the things we want to do is not just have data, but to be able to project into a future that we haven't experienced yet. If you're in the lab and you're working on a set of data, you can measure parts of the experiment and use information you already know to figure out other parts of the experiment you haven't done yet. So here we have Clapeyron, two scientists who work together to figure out what is called the two-point form version of the Clapeyron equation. So I'm just kind of going straight to that. If you read the textbook, they give you more information of how they arrived here. Okay? You pretty much take this right here, get the equation of the graph, and the y is equal to mx plus b form. And then you do this twice, and then you combine both equations to get this right here. Okay? So this equation, as we saw yesterday, is useful to help us, is used to solve for either P1 or P2, depending on the question. So if you have pressure under one condition and you have temperature under the same condition, you're trying to figure out how the pressure changes from the temperature changes, then you're solving for P2, right? You want to know delta H, the enthalpy of vaporization or fusion, depending on what you're looking at, okay? And then you want to know what R is. So the purpose of this equation is to help you solve for the unknown. Now the unknown can be so many different things. It can be P1, P2, T1, or T2. And this equation, as it says here, is used to measure vapor pressure and temperature. Okay? So they're saying that you can be given P1, P2, T1, and T2. And if they give you all that, it says the equation can be used to predict the vapor pressure if you know the heat of vaporization and the normal boiling point. Remember, the vapor pressure at the normal boiling point is 760. So when they say normal, they mean 1 atmosphere or 760 torr or 760 millimeters of mercury. Pick whichever is relevant to the question, because the question will give you different units for pressure. Okay. Now we worked on this yesterday, but now we're going over it in context. Okay. So yesterday we worked on a different problem, right? And today, let's see, what is the vapor pressure? Yeah, yesterday we're solving for, I forget what we're solving for, but today we're getting to solve for pressure. So we'll see how this works out. We'll work everything out. And then we'll compare our answers with their answers. When you're watching me on video, please make sure you're working this out yourself. Because it's one thing to watch me use my calculator and figure things out, and it's something else for you to do it yourself, right? So we're told here, I'm going to write the equation out, or I can just copy it. Let me be a little lazy and copy it right here. Okay. So I have this. And then in this question here, we're told we're dealing with methanol. So methanol has a normal boiling point of 64.6 degrees Celsius. So I'm going to write here, T1 will be my normal boiling point of 64.6 degrees Celsius. Okay. If it's normal boiling point, then it's going to have a pressure. I'll put pressure 1 here, but I won't write it yet until I read the rest of it. And a heat of vaporization. So I know with T1 comes T2, right? And P2. So I'm going to leave that there. But it says heat of vaporization, delta H of sub VAP. This is equal to 35.2 kilojoules per mole. What is the vapor pressure of methanol? So we're looking for this at 12 degrees Celsius. So we got 12 degrees Celsius. Okay. Since they didn't give us the units of the first vapor pressure, the more common one is millimeters of mercury or torr. Since they use torr here and I want to compare my answer with their answer, I'm going to be consistent and say this is 760 torr. Now, if it's a question, if it's a multiple choice question, look at the units of the answer before you actually continue from here and select your pressure. Okay. If the answer is an atmosphere, use 1 atmosphere here at P1. Okay, so I think I have everything I need. Oops, one more thing. I need R. For this question, because remember from 1411 we had 2 R's, right? 2 major R's we worked on. 0.08206, right? And then R equal 8.314. The units for these R's are different, right? And the context is different. For the first one, since I wrote here, I don't have a lot of room. It was liters times atmospheres over a mole times K. I wrote this so much I memorized it. This one here is joules over moles K. So let me spend some time on this, reviewing 1411, right? You use the second one if the context of the question has heat. Because there's a joules here, you use the second one. It's more appropriate. You use the first one if the context of the conversation has some kind of pressure in atmosphere, and there's some kind of leader. So usually the first one is used when you have gas, like real gas, not vapor, but gas. And you're measuring pressure in atmosphere, things like that. The first one is more relevant. If you have joules or some kind of measurement in joules, stick with the second one. Okay. So now I've said that, let's go back here. R equal 8.314. Did I always get this when I was a student? No. But then I actually picked an R I liked. I really liked the first one, this one here. I was weird like that. I like this number. From now on, I'm going to use this. And then I realized I can't always use that. So that helped me to recognize that there were many R's. And my teacher gave me like 4 R's. And like, why do I need all these R's? Can I just pick one I like? You know? Okay, so we are trying to work on this problem. Like I said yesterday, you want to take this equation right here, and you don't have to do it the way I do it. It's a lot easier for me to teach it this way, divide it in 3 parts, right? So you have the middle part, you have the left part, the right part. Since what we're solving for is right here, I will deal with the left part later. I will start with the right part, okay? So I'm going to start with negative delta H over R. I'll start with this. Oh, one more thing I forgot to mention. Your units must reconcile, right? Your units must reconcile. So let me do this. Let me write this. Oops, 64.6. Temperature 1, 64.6 degrees Celsius. Temperature 2, 12. I was being a little zealous when I started to plug in the calculator and stuff, and I was like, wait, I haven't converted my units. And then this one here, 35.2. This is 35.2 kilojoules per mole. Okay? So we're trying to reconcile our units, right? Most of the time when talking about reconciling the units, the constant will give you a clue into what the other units should be. So looking at this is K, right? That means your temperature should be in Kelvin. So convert 64.6 to Kelvin by adding 273.15, right? I have, oops, wrong marker, 337.8 Kelvin. Same thing with this, 12 plus 273.15, 285.15 K. Okay, so I have worked on the temperatures. They have the units actually reconciled. Now the next thing I have to do is look at the joules, right? This is joules, this is kilojoules. So I have to convert delta H VAP to joules. The mole and the mole are fine. Okay, so I'm going to rewrite this as joules. That means I take 35.2 times 1,000. And now I have it in joules. 35200 joules per mole. Okay, joules per mole. There. Now my units reconcile. You're probably wondering, if you're an overthinker like I am, what about torr? That just means when I get my unknown will be in torr. Okay, we're good. Okay. Now that I've done that, finally I can start working over here. So I can just copy this number in negative 35200 joules per mole over R, and R is 8.314 joules per mole K. This cancels out, this cancels out. My answer will be some number in K, right? So it'd be K is a denominator of a denominator and ends up being a numerator, K. So let's see, my answer will be 35200, the negative. Oops, I wrote in the wrong place. Negative 35200 divided by 8.314. Okay, so I get negative 4233.8, right? Okay, are you with me there, Jacob?
Yes, I'm here.
Okay, just a little quiet. I know the afternoon is different from the morning, right?
Yes.
Okay. Yeah, hopefully the next time we do this, yeah, it will be much earlier, but that's okay as long as you're still with me. So I solved this first part, remember? Now my next one is this part here. I want to do 1 over T2 minus 1 over T1. Oh, I see what they did here. That's why we're using this formula. Okay. The formula we're using today is slightly different from the one I used yesterday, but they're the same. It's just that this is T2, T1, P2, P1. But you know what I'm doing, right? So I take 1 over T2, 285.15 K minus 1 over 337.8 K equal to, okay, 1 fraction 285.15 to the right minus 1 fraction 337.8 to the right equal. Okay, I get this number 0.00054 uh, 66. Okay, and this is 1 over k. So now these are both on the right. I've done that part, I've done that part. So I can now combine them and say ln P2 over P1 is equal to, the first number was negative 4233.8K times 0.0005466, 1 over K. So you see how the units cancel out to where we have no unit? Then I still have the second number on my calculator, so I just write times negative 4233.8 multiplied by the first number, and I end up with negative 2.3141. I have log natural P2 over P1. Woo! Okay, we're doing good. We're doing good. Now we're trying to solve for P2, right? So we have to get rid of the log natural. To get rid of the log natural, take e power, how does it look over here? E power x of both sides, right? Or e power whatever of both sides. That's what I'm doing. So what's happening here, that helps to cancel the ln out, and I'm left with P1 over P2 equal e power negative 2.3141. So when I select that on my calculator, I get e power the answer. I get 0.09884. So, oh, I switched these around, didn't I? Oh, man. P2 over P1. So P2 over P1 is equal to this. So P2 is equal to P1 times 0.09884. P1 is essentially, what was P1 again? It's been so long since I saw this number. 760. Okay. 760 times that number, 0.09884. So the unit here is torr, of course. I should actually make this give me some room so I can write the unit. 760 torr. And so this number times 760 gives me 75.1. Let me see how many significant figures I have. I see 3 here, I see 3 here, I see 3 here. Okay, 75.1 torr. So P2 is 75.1 torr. I know. Such a mental marathon. Yes, I had to learn that in oh my goodness, in college. My teacher, he could teach for like 4 hours straight, and by hour number 2, I'm like, I'm fading. How are you, an older person? And then I got to grad school, and I'm like, oh my goodness, what is this? What is this? Cross country. It was like a mental marathon. We just kept working and working, but it helps you build endurance. Anyway, we go through all of that. Their abbreviation is slightly different because, they rounded numbers up early. 754 torr also. Okay. Once again, remember to kind of keep track of what's going on and remember what units to convert your units to. Remember 8.314 joules per mole K. Temperature has to be in Kelvin. Any energy unit has to be in joules, and then go from there. Okay, all the units will cancel out. It will reconcile, and it should work out. This is what we worked on yesterday. I'm not gonna even mess with that. So I'm just gonna scroll, scroll, scroll. I don't want to change it. And then some more stuff we worked on yesterday. Scroll, scroll, scroll. Oh, here. This was relevant yesterday. Okay, so now we're talking about solids, right? It's talking about sublimation and deposition. Sublimation is going, it says here, molecules in a solid state vibrate. The surface solid molecules with sufficient energy may break free. There we go again. It's like the molecules are not happy being held back by intermolecular force. It almost seems like intermolecular force is some kind of unhealthy relationship, right? Because all you're seeing here is all these molecules trying to break free. Like, please help, free me, right? So the molecules on the surface of the solid this time, not even the liquid, are breaking free and they're becoming gas. So we have a situation here where we have a container, we have a solid, and the molecules on top are breaking free to form gas. They're not even forming a liquid, they're going straight to gas. This process is called sublimation. So going from solid directly to gas without ever forming a liquid is called sublimation. Okay. Then the reverse, going from gas, going straight to solid, is called deposition. Like a deposit, deposition. The capturing of vapor molecules into a solid is called deposition. Okay. So you're going the reverse. This is kind of like a cold winter morning, which we can imagine this, right? We did have snow that one day. That one day. If your car was outside, you may have experienced this where because the temperature was very low, you had moisture in the air and it actually solidified. It deposited on the windshield of your car and formed ice. Yeah, that would be deposition. Straight from vapor into that kind of like I forget what it's kind of ice, but you have to scrape it off. That stuff. Okay, so we're told melting fusion essentially is going from solid to liquid, right? As the solid is heated, the temperature rises, the molecules vibrate more vigorously. Once the temperature reaches the melting point, the molecules have enough sufficient energy to overcome some of the attractions that hold them in position, and the solid melts. So here, versus the first little paragraph, this second scenario here is talking about a solid melting. So the solid becoming a liquid. You have to apply heat, giving the solid molecules enough energy to break free from the attraction that was holding them back in position. So, of course, melting is the opposite of freezing. This is melting. And then freezing is going from liquid to solid, right? This is freezing. Okay. Then I see that I have space here. Oh, so finally the heating curve. Now we talked about this yesterday, right? Talking about the heating curve, saying as you heat the solid, the temperature first increases linearly until it reaches the melting point. So I drew this yesterday, showing you what's happening here. In this graph here, you have a graph showing you y-axis temperature in degrees Celsius versus heat that's going to be added. And what you're trying to do is you're trying to add heat to the compound, the solution, the chemical in general, and then watch what's happening to the temperature. You're measuring the temperature, right? So if we're starting at this point right here at negative 10 degrees Celsius, I can say from this picture, we're starting from negative 10 where you probably have a frozen solid. And as heat is added, right, because heat is increasing, it goes from negative 10 degrees to 0 degrees Celsius. So the heat of the compound or the solution of whatever it is that you're heating up increases until we get to 0 degrees Celsius. Now, I can almost hypothesize this is water because water is the one that melts at 0 degrees Celsius, right? At 0 degrees Celsius, like I said yesterday, melting takes place. In the beginning, you have a solid here, a solid there. At 0 degrees Celsius, we go from solid to liquid. Okay. At that temperature, Even though you're still adding, it shows right here, you're still adding heat. But when you measure the temperature, there's no change. It's like nothing is happening. You're figuring out what is going on with all this energy I'm adding. Am I just wasting energy? No. Here at melting, energy is used to break bonds, to break intermolecular forces, converting solid to liquid, right? The energy has a purpose. It's being used at that point to break intermolecular forces, converting the solid to liquid. Because the whole time you were heating up the solid molecules, they were absorbing the energy and storing it, right? Now they use it to break free from the chains that held them back. They're not really chains. I'm just trying to dramatize it from the intermolecular forces that held them back in place, right? Then over here, remember I mentioned this yesterday. Anytime we have a difference in temperature and you're asked to figure out the heat change, use this equation right here. Next one over here is boiling. So once you have melted your solid, now you now have a liquid. You increase the heat from 0 degrees, right? Increase the heat of the liquid, go up and up and up until you get to 100 degrees Celsius. Once again, I'm thinking this is water. At 100 degrees Celsius, we have boiling. Boiling takes place when you're adding heat. The heat is being absorbed by the chemical and is being used to once again break bonds. Heat added, used to break bonds. And this all happens at 100 degrees Celsius. So if you measure the solution or the liquid, there will be no change in temperature because all the energy is being focused on breaking bonds. And here I mean intermolecular forces, right? To allow the liquid to become a gas. Free. So during melting and during boiling, in the point of melting, where the heat is being added, we're told heat of fusion is the amount of heat energy required to melt 1 mole of solid. So in the flat portion, when the solid is becoming a liquid, essentially the heat being applied is essentially used as heat of fusion, the heat required to melt. Okay? At the point on the graph where you have a liquid becoming a gas, the heat applied is being used to vaporize the liquid. The amount of heat energy required to boil 1 mole of liquid. Okay? And since you have to add heat to have melting, and you have to add heat, this is melting, right? Melting, this right here is boiling. Since you have to add heat to have melting or boiling, the symbol for this is positive. That just means you have to add heat. Add heat. Okay? Okay. So this is where we've kind of gotten to. We worked on a different problem yesterday. I want us to work on this together today. I feel like I'm actually making a lot more progress than I thought I was going to make today. Okay? So this is not bad. We're making some progress. That means that tomorrow, if I don't get all of this done, I'll finish phase diagrams tomorrow and then we'll continue with the rest of the lesson. Okay? So I worked on a question similar to this yesterday. I'm going to be working on this today, where it says calculate the amount of energy required to heat 1 mole of water from negative 25 degrees Celsius to 125 degrees Celsius. So since I'm dealing with 1 mole of water, and I'm going from negative 25, that's very cold. Let me draw my graph here. My straight lines are hard to draw. Okay, so negative 25. This is water, right? So you want to include the freezing point of water, 0 degrees Celsius, then boiling point, 100 degrees Celsius, then the other temperature, 125 degrees Celsius. Okay, so this is temperature right here. Temperature, the one that you measure in the lab, degrees Celsius. On the right or on the horizontal axis, what I have here is you're adding heat, heat added, okay? And what changes are we going through? So first, when you add heat at 25 degrees Celsius, we see the sample getting warmer and warmer and warmer until it gets to 0 degrees Celsius. At 0 degrees Celsius, the temperature doesn't change that much as it melts, right? Then again, Once it's done melting, it starts to increase in temperature again as you add more heat. When you get to 100 degrees Celsius, what happens again? It starts to change phase from liquid to gas. And this goes on for a lot longer because it requires more energy. Then finally, we have that last transition all the way here to 125 degrees Celsius. Oh, wait, that last step can be a little bit more straighter to match with everything else. Come on. Let me hold this here. Yeah, that's more like it. Okay, so now we have our steps, 5 steps. Now, I mentioned this yesterday. Step 1, step 2, step 3, or segment 1, 2, 3, 4, 5. We need all 5 segments, right? Because we're going through the whole process. Remember, I mentioned this yesterday. 1, 2, and 3. 1, 3, and 5. I'm saying 1, 2, and 3, and I'm pointing at 1, 3, and 5. Segment 1, 3, and 5 all show a change in temperature. So segments 1, 3, and 5, because the temperature is changing, we use Q equal mCs delta T. And for segments 2 and 4, use Q equal N delta H, whatever it is, okay? For the flat parts of your graph, you want to use Q equal N delta H. And you have the information. Now remember, in segment 2, you have melting, which is called fusion. And then segment 4, this is vaporization, which is boiling. Vaporization. If I can spell correctly, this will be a good thing. Okay, I want to show the physical state so it helps me to keep focus and not forget what I'm doing. At negative 25 degrees Celsius, the water is frozen. At 0 degrees Celsius, it's still frozen. At 0 degrees Celsius, finally it starts to melt. It goes from solid to liquid. Step 3, it goes from liquid to liquid, doesn't change state. Step 4, it goes from liquid to gas. Step 5, it goes from gas to hot gas. So at step 1, 3, and 5, the physical state does not change, but the sample just gets really hot, and that's what we see right here. Okay. Let me go ahead and add pages here so I can freely write, and then in the end, we'll compare our answers to the answers they have. Even though if I remember correctly, they don't add all the masses or all the Q's together, so yeah. Anyways, let's see. We'll do number 1. Number 1 here, Q1 will be equal to MC. Q1 is in the frozen section, so C ice or solid. Let me say solid because the question says solid here. MC solid times delta T. Okay? So let me see. So Jacob, you remember us working on this yesterday? This question?
Yes, I do.
Okay. Since you've been extra quiet, I want you to go ahead and help me with this part here. So in this question, the amount of water I have is 1 mole, right? I have 1 mole of water. Here's the thing. This M stands for mass. So how do I get the mass of water from 1 mole of water?
You get the molar mass.
Bingo. We do the molar mass, 2 hydrogens and then 1 oxygen, so we end up with 18 grams, right? Very good. So even though they said 1 mole of water, when I need mass, I just get the molar mass, like he said. So this is going to be 18 grams of water. And then I have to find C solid, right? C solid will be this number right here, this top one. 2.09 joules grams per degree Celsius. Okay, now what is my delta T? What is my final temperature and an initial temperature? What are they? This is the graph right here. What do you think it is, Jacob? We're dealing with only segment 1. So at what temperature are we starting for segment 1, and where do we end for segment 1?
Negative 25 and 0.
Okay, great. Okay, so you're quiet because you got this. I'm like, am I boring you? Okay. So wait, we end at 0, right? Because it's temperature final, but we started at negative 25. Okay. Good. Right there. So now we're gonna be working this out. Yeah, but you see how once we work the one from yesterday, you see how routine it is?
Yes, it is.
Okay. But the homework questions may not always show you the whole transformation, so you have to read that part carefully. Okay, I think these two here give me 25, right? Times 25, because it's negative, negative. Okay, so I'm getting 940.5 joules, because the gram and the gram cancel out, the Celsius and the Celsius cancel out, and I'm left with joules. So Q1 is done. Yes, done. Second one, fusion. Fusion, I have to do Q2. Oh, I like to separate these visually because it becomes a lot. Q2 equal number of moles and then delta H fusion. Number of moles, they said it was 1 mole, so I'm going to write here 1 mole. And then times delta H fusion, where is the words right here? 6.02. Really, kilojoules? 6.02 kilojoules per mole. I'll leave it as that. I'll convert them all to the same unit in the end. 6.02. Okay. So this will be oh, same number. I was gonna use my calculator and I was like, really? 6.02 kilojoules. Well, let me not be super lazy. So this one here is in joules here. I can either convert this. Let me convert the first one to kilojoules. So once I got this, I'll convert this one here to kilojoules. 1 kilojoule equal 1,000. So divide by 1,000, divide by 1,000, and I get 0.941 kilojoules. So the second one can be in kilojoules. Okay. And I'll just highlight my heats. Okay. Much shorter process. Q3.
The point. Hold on, let me do the math 'cause that seems a little bit weird.
Okay.
Uh,
Sounds good. Yes.
get break.
You what?
Break.
Yeah, because I'm like, what happened to this partnership that we have?
Oh, I'll divide, right? There you go.
Yeah.
940.5 divided by 1,000.
Yeah, because when you're watching me, it's like,
Yeah, you're right.
yeah, bro.
You're right.
Yay, thank you. Okay, Q3. Where's Q3? Q3, we're going from 0 to 100, right? Oh, but we need to, okay. So Q3, we need to use M, but we need to use C of the liquid. Then we're going from 0 to 100. So the final is 100. The initial is 0, right? Because it's always final minus initial degrees Celsius. So my mass is still 18 grams. I have to find C liquid from the list. I use this. I already used that. C liquid is 4.18. Make sure you don't confuse those C's, right? Because they're all different. 4.18 joules per gram per degree Celsius times, when you subtract this, you get 100 degrees Celsius, gram, degree Celsius cancel out, gram cancel out. We get our answer in joules. Okay, yeah, do the math with me so we can confirm, because you know how I get, right? 18 times 4.18 times 100. Okay, I got 7524. I'm just going to divide by 1,000 since I came this far. And it says I have 7.52 kilojoules. Is that what you get?
Hold on.
Okay. Because if you double check my work, I don't have to double check my work.
75.24.
Yep, that's what I got for kilojoules, right? So
Yeah.
that's Q3. Okay, let's work on Q4. Q4 is one of those that has a shorter process, number of moles, this time delta H, VAP, So number of moles was still 1 mole, right? Delta H VAP. I just used this one here. Done with this. Delta H VAP 40.7. So that should be no problem here. 1 mole times 40.7 kilojoules per mole. Mole cancels out. Our answer is 40.7 kilojoules. A lot of kilojoules there. But a lot of work is being done to separate the molecules, free them. Finally, Q5. Q5 is mass again, C gas, delta T. This time we're going from what? 100 to, I think it was, final was 125, right? And then we came from 100. Let me verify this because sometimes I look over there and I'm like, yeah, 100 to 125. Okay. CS of gas is 2.01. We'll use that one. 2.01 joules per gram per degree Celsius. The mass is still 18 grams. It hasn't changed. 125 minus 100. Oh, by the way, somebody said that they appreciate your participation in the class.
What happened?
Somebody said they appreciate your participation. You know how you
Oh,
talk to me during the lesson, so they feel like they watch the video because they can't log in during the session because of the time difference, and they said
yes.
they appreciate your participation. So I wanted to
Um,
make sure your voice was heard, and
yeah.
nobody thought I was here by myself talking to myself, right?
No, that's good.
Okay. So I got 18 times 2.01 times the difference here is 25. So times 25. So we have 904.5 Q5. This is joules. Divide by 1,000 is 0.9045 kilojoules. Okay, we gotta add Q total. You gotta add them all. So Q1 plus Q2 plus Q3 plus Q4 plus Q5. Okay, Q1, 2, 3, 4, 5. Okay, you know, as I've gotten this far in the PowerPoint slide, I'm thinking we haven't talked about solubility in that question yet. So I will go ahead and answer that question just because you asked me. Okay. But I
Uh,
realized that we haven't covered the content that allows you to answer the question you were asking me about. Okay, this is Q5, and Q5 is 0.900. What's Q4? 40.7. I know, I'm writing backwards. Kilojoules. Because I can actually see these numbers right here. Then 7.52, 7.52 kilojoules. Then that's Q3, 6.02, 6.02 kilojoules. Then we have Q1, which was 0.941, 0.941 kilojoules. Okay, so the last one plus 40.7 plus 7.52 plus 6.02 plus 0.941. Okay, I got 56.09 Q total. Okay. Any questions about this?
no, ma'am.
Okay, yay. So they went through and yeah, I mistakenly added a page there. They went through so we can now delete that page. Yeah, they went through, did all the math here, shows you how they convert to kilojoules, did all the math here, here, here. I don't think they actually end up adding them all together. So here's the thing. I don't want to do the phase diagram today. I want to do that tomorrow with the rest of the class so I can finish this up and then we start the what's the next chapter again? The next chapter is
That's rough.
solids. Yes, the solids. I want to do that one tomorrow with But you know what? I wonder if I'll have enough time. I wonder if I'll have enough time. Anyway, let me do this. Let me answer your question that you asked earlier, and then we'll end on that. The phase diagram part here doesn't take that long because it's really not that complicated. Yeah, I should be done with this in like 15, 20 minutes. And I can finish the rest of this. Okay? So tomorrow I'm going to write myself for myself a note saying start here. Okay? But what I'm going to do instead is add some pages here at the end, or it doesn't really matter where I add them. I know where I'm going to be starting. So let me add the pages in between these because in the end, nobody gets access to these pages anyway. To answer your question, right, you were asking about the solubility. I just realized it's different because whenever I'm talking to you guys about a question and then I go over it in context and I can tell better, but it's usually after the fact, not before. So we're looking at number two. Number two says draw Lewis structures of hydrochloric acid. So I'm going to be drawing hydrochloric acid. I have to draw Lewis structures. Let me see. Oh, you know what? No, we are able to answer this question. Okay. I was thinking something completely different. So draw Lewis structures of AHCl, because I actually just copied this from online. I found that online. I need some space. B CH3 CH2OH. That's ethyl alcohol. And then hexane. C, C6H14. Okay. Then they're asking us about which of the liquids above are soluble in H2O. Okay, so this question is really about like dissolves like. Okay. So we're drawing Lewis structures, but ultimately our goal is about like dissolves like. That's the purpose of this question.
Where's your
Okay.
other screen? I can't see it.
Oh, I'll show you in a moment. I just need to get this. So these are our Lewis structures. And then the solvents, I'll draw them on the side. The solvents will be carbon tetrachloride, or water first. Yeah, I'll show you in a moment. H2O, and then carbon tetrachloride. Okay, so here. Okay. So this the question we're looking at is really about like dissolves like. First of all, these are our solutes. So they want us to draw the Lewis structure first. Then these are our solvents. And the question is which one goes with which? So let me start with the left side. Lewis structure. So hydrogen, I only have one, right? And hydrogen is in group one. So that's one. Chlorine, I only have one in the structure. Chlorine is in group 7, so I have 7 here. I add this up, I end up with 8 electrons. When I'm drawing this, hydrogen cannot be in the middle, so chlorine will be in the middle. Hydrogen will be on the outside. I use 2 electrons to form a single bond, minus 2. I'm left with 6. I use 6 around the central atom because hydrogen can only form a single bond and obeys the do-it rule. So I put 1, 2, 3, 4, 5, 6. Minus 6, this is 0. So my Lewis structure is H-Cl and then the 6 dots. Next. This one here, this is an organic compound. They tend to give you not the full structural formula, but the condensed formula in such a way that you can figure out the structure. So I want to highlight here. The way this is written, the carbon is central, the oxygen is central. So you can see that molecule as having 3 parts, okay? With the 2 carbons being central. So you have carbon, carbon, and then oxygen. Now I have to do my electrons, right? Figure out my total valence electrons. In the formula, I have carbon. And let me see, let me draw this a little bit to the right. I need some room. Carbon, carbon, oxygen. Carbon, wait, 1, 2, I have 2 carbons They're in group 4, so I end up with 8 valence electrons, right? I have 1, 2, 3, 4, 5, 6. I have for hydrogen, I have 6 of one, so I end up with 6 valence electrons from hydrogen. For oxygen, I have 1, right? But this is in group 6, so I end up with 6. Okay. So with this, I'm working with, hold on, 8 plus, I am not doing that in my head, 8 plus 6 plus 6 because of mental fatigue. I am working with 20 electrons. So I'm going to write this in the top here so I can keep track of it. I'm working with 20 electrons, right? I may want to move this a little bit to the right because I want to have enough room to write my formulas. Oops, I'm not drawing bonds yet. Not yet, not yet. Don't get ahead of yourself there. Okay, I'm working with 20 electrons. So I have to connect the central atoms first. Connect, connect. That used up 2 bonds. 2 bonds equal using, remember each bond uses 2 electrons, right? So 2 bonds uses 4 electrons. Total 20 minus 4, I'm left with 16. I need the middle. Now I need to fill in the rest. I have 3 hydrogens here. 1, 3, right? I put hydrogens around the first carbon, and each time I did that, I added a bond. So 1, 2, 3, that uses how many? 6 electrons. So I now have 16 minus 6, I'm left with 10. Then I have to add the 2 hydrogens to the carbon in the middle. I put a bond there, add the hydrogen, put a bond there, add the hydrogen. Those 2 bonds use up 4 electrons. So 10 minus 4, I'm left with 6. 6 electrons. And then I have 1 hydrogen right here. When I put the hydrogen on the right of the oxygen, I have to draw a bond so that uses up 2 electrons. I'm left with 4 electrons. Since I'm not adding any more atoms, I don't have to add any more bonds. The remaining 4 electrons go on the oxygen like lone pairs. So now, except for hydrogen that obeys the duet rule or duet law, all the carbons are surrounded by 4 bonds or 8 electrons. The oxygen is surrounded by 8 electrons through 2 bonds, 2 lone pairs. Okay, Lewis structure. So for the sake of what I'm about to do, I'm going to erase this. That was a means to an end. I don't want all this stuff here because I have more stuff to add. Okay. Last one, 6 carbons. Ooh, carbon. I have 6. Carbon is in group 4, right? That's going to be 24. Hydrogen, I have 14. This is in group 1. That's going to be 14. 24 plus 14 is a huge number at 38. 38. Okay. Drawing my Lewis structure. 1, 2, 3, 4, 5, 6. 6 carbons. I'm actually going to add my hydrogens around it. So 1, 2, 3, 4, 5, 6. Remember, in 1411, carbons tend to naturally be in default mode surrounded by 4 bonds. Okay, so if it makes it easier for you at this point, you can bring in 3 hydrogens here so you can see how the 4 bonds work out like that. Okay, so if it makes you feel better, I don't know which one is better for you guys as you're learning this, or you're relearning if you've forgotten. You can add the 4 bonds around the hydrogen and you can see how that works out. The 4 bonds around each hydrogen. Okay, then you can bring in the hydrogens here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I use all 14 hydrogens. All 6 carbons, all 14 hydrogens. Now the other question I have to answer is, did I use 38 electrons? I want to make sure I did this right. 6 carbons. Each carbon is 4. 14 hydrogens. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Did I miss? Oh, I missed some of these. 'Cause I'm like, this doesn't look right. Hold on, I missed some of the bonds. I wasn't counting right. Oh, yeah. After we're done with this, we're done because if I'm not counting right, this is not good. Let me count from the beginning. 19 bonds. 19 times 2 is 38. Oh, okay, we got it. Correct Lewis structure. Okay, when we're talking about like dissolves like, we mean like intermolecular forces dissolves like intermolecular forces. So don't forget, this chapter was about intermolecular forces. So even though I drew the Lewis structure here, the question I have is, does this have London dispersion force? Is it dipole-dipole? Does it have hydrogen bonding? We're asking that of every molecule. And we're going to focus on the dominant bond. So for HCl, what do we think it is? Is it London dispersion force, dipole-dipole, hydrogen bond? Let's start from the strongest. Does HCl have hydrogen bonding?
Yes.
HCl?
Yes.
Remember, hydrogen bonding happens with OH, NH,
Oh,
FH.
oh, I'm sorry. I'm sorry.
That was yesterday. So no, right? I know chlorine is a relative right below fluorine, but chlorine is not as selfish as fluorine, right? The elements that are doing hydrogen bonding are not just polar, they're super polar because they're very selfish. So chlorine is not that bad. Okay, so for that reason, no hydrogen bonding. But because you have two different elements, if you had two same elements, it would be nonpolar. If you had this scenario here, nonpolar. If you have Cl and Cl, also nonpolar, right? But since you have H and Cl, you have polar. So if anything at all, this one here is going to be dipole-dipole, the strongest intermolecular force, or you can just call it polar. So we'll call this polar. Okay. We tend to name the molecule, except for the ones that have hydrogen bond, by the strongest intermolecular force. Okay. So this is going to be polar. Next one. In this molecule here, the second one, once again, same test, hydrogen bond, dipole-dipole, and then LDF. Does this second molecule here, does it have hydrogen bonding? This B? In the Lewis structure, look at the Lewis structure. Do you see hydrogen bonding here?
I think it's what were those three things again? OH.
O dash H,
Yes.
N dash H, and then F dash
Yes,
H.
it does.
Right. Okay. So here's the thing. I know as you're memorizing this, it's hard to memorize out of context, right? So here's kind of I used to write it a lot because I'm bad at memorizing. I would write it down a lot. Then later on, as I grew up and I learned more chemistry, I realized in the periodic table right next to fluorine, if you look at fluorine, right before fluorine, there remember the SNOF group? If you attach an H to this, an H to this, and H to this, you got the three we're talking about. Carbon dash hydrogen is nonpolar. So starting from nitrogen, oxygen, and fluorine, NOF, you add H to each of those, it gives you the hydrogen bonding elements. Okay? So in that group of four, SNOF, carbon cannot hydrogen bond, but the rest of the three can. Okay? So yeah, back to this one here. Where was I? Right here. You see that right here? Hydrogen bonding. So this can hydrogen bond, it can hydrogen bond. I mean, hydrogen bond, dipole, dipole, LDF. So I'll say here, this can hydrogen bond, right? And it's also polar. So I'll write these two just because when it comes to solubility, that matters. Okay? It can hydrogen bond, is polar, and it also has LDF. So these kind of all matter. So we'll continue. Next, C6H4. Do you remember what I told you about organic compounds that have carbon and hydrogen only? What they are? Because this compound fulfills that criteria. It has carbon and hydrogen only. It doesn't have any of the other heteroatoms. They tend to be non-polar. Okay, when they have carbon and hydrogen only, because remember I just told you right now, in the SNOF group, If you attach hydrogens to all of these, the ones on the right are not only polar, these are polar and can hydrogen bond. This carbon here, attach a hydrogen to it, and somehow it works out to be nonpolar. Yet it keeps, it's right next to that group right there, but it's totally nonpolar. So the carbon hydrogen bond is nonpolar, even though carbon is right next to nitrogen in the periodic table. Crazy stuff, huh? But it's nonpolar. So most of the fats we have, I'm thinking of fats right now. You know, the greasy, the avocados, all the great fried chicken, all that greasy stuff we're told not to eat. Avocado is good, but the other stuff, usually that's the nonpolar stuff, right? Yeah. It does taste good. It does taste good, but it's not very good, right? This is the greasy stuff, your oils and stuff. So bottom line, this is nonpolar, and the most dominant force here is LDF. Okay, after all that dialogue, let's come to the right side and see what's going on here. On the right side, now we have our solvent. Look at our solvent. Of course, we know about water from before. I won't go through everything for water. Water is definitely polar, right? Water is polar. You see how it has the two lone pairs here? This is polar for water. And then CCl4. For this one here, I'll work it out. Carbon is 1, group 4. Chlorine, we have 4, group 7. 4 times 7, 28. Add these two, 32. So we got chlorine. I need the space right here. Chlorine in the middle. We got, not chlorine in the middle, sorry. Carbon in the middle. We got 4 chlorines. And we have 32 electrons to distribute. 1, 2, 3, 4. 4 times 8, 4 times 2 is 8. So we got 8 electrons here. 32 minus 8. Yeah, I'm getting fatigued already. 32 minus 8.
24.
Thank you. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 4 is 24. I just used all electrons, right? I'm out. Now I'm judging the lowest structure. Central atom has no lone pair. So it's based on that alone, it's nonpolar. The surrounding elements are all alike. So this is definitely nonpolar. LDF only. Okay. So based on the intermolecular force, which one goes together? What does this last one go with? Let me see if I can use a different color. This last one that has LDF only. Which solvent does it go with? Does it go with water or does it go with CCl4?
You said track.
Yes, they have to be alike. Yes.
Okay, so LDF goes with LDF.
Okay. So let me use a green color. This goes with this. It would dissolve. If you're in the lab and you're asked to pick a solvent that will dissolve, that goes with that because it's LDF and LDF, right? Very good. Now, let's see. What about the first one, HCl? What can we say about that?
It's polar, so it attracts the polar.
Right. It attracts this one here. Now remember, this one also hydrogen bonds. The water also hydrogen bonds, right? Because it has 2 hydrogen bonding sites, so it also hydrogen bonds. But because this is polar, this can actually dissolve in that. So this will go with water, right? And then what about the alcohol? The second one, the alcohol.
Alcohol dilutes in water, so
Okay, yep. Alcohol. Ah, you go by experience. Go by the chemistry. Stick with the chemistry. You're like, I'm like, we didn't talk about dilution. I know what you're doing. Stick with the chemistry, but yeah, so the alcohol will go with the water too. Okay, so we haven't learned this other part yet, but the alcohol will actually go with both. The alcohol will go with water and it will go with CCl4. Just
yeah,
because you see how this part here, you see this part? It's
yeah.
kind of like that. So it does have a strong LDF presence. So the part that's really, really LDF E will go with that part. So it can actually dissolve both ways. It can dissolve in that, it can dissolve in water. So we'll cover that in chapter 13, I think.
Well, you should automatically know that alcohol dilutes in water. I mean, if you do tequila shots, you would know better.
Some people taking this class are not drinking that, they're not consuming that beverage, or they shouldn't be, at least. They shouldn't, I'm just saying. Right. Yeah, so that's all the chemistry behind, just to say you can mix the alcohol with the water, right? And people say I overthink things. I'm like, I'm not overthinking things. This is chemistry. You gotta do all that stuff. But sir, this is as far as I'm going today.
Okay.
Tomorrow, when we get our rest and we're all fresh and stuff, hopefully there's not a lot of drilling tomorrow, so we can go ahead and continue this part and then go over phase diagram. Not phase diagram, sorry, the solids. Solids is actually, I think it's kind of fun. And then you'll be able to get caught up. So after this part, you can get caught up with both labs from this Sunday and also work on the lab from this that's coming up this weekend. Okay?
Okay. All right. No worries. I'm already on my
Okay.
bed, so I'm good.
Okay.
All right. Thank you.
Okay, then I will see you tomorrow.
All right. Bye bye.
Okay. Bye.